Welcome to a new AG session all about analytic geometry. This time, we are going to show that the given points A at 3 and -6, B 8 and -2, and C -1 and -1 are vertices of a right triangle. In this given Cartesian plane, let's try to illustrate these 3 points. If we are going to consider each grid by 1, and of course the horizontal axis is our x-axis and the vertical as our y, our first point A can be found here. 1, 2, 3, and I have -6 for y. 1, 2, 3, 4, 5, and 6. This is point A at 3 and -6. B, on the other hand, is at 8 and -2. That's 4, 5, 6, 7, 8, and -2 here. This is B. And finally, our point C is at -1, -1 here. This is our C. If we are going to connect these points, we will have here a triangle using these 3 vertices. So we'll have it here like that, and here as well. And we are going to show whether this is a right triangle, probably thinking about this angle here being 90 degrees. We are going to show here a specific step which include the concept of distance. Of course, if we talk about the right triangle, there exists a 90-degree angle, and that means we have segments that are perpendicular to one another, and we could use the concept of slopes by the relationship of 2 slopes of lines that are perpendicular to one another. But in this case, let's use a different method. We are going to use here the concept of the Pythagorean theorem. Okay? Of course, after this, we have our triangle. It's still called A, B, C. And we have our segments here. Segment AB, okay, as its side, this one. We also have segment BC, okay, and segment AC as the 3 sides of our given triangle. In connection to our Pythagorean theorem, we are going to establish that this is a right triangle if we could come up with a relationship that the measurement of the longest side, calling as a hypotenuse, the square of that is equal to the sum of the squares of the other 2 segments. Of course, we can verify that by first solving for the length of segment AB, BC, AC, or side using the idea of the distance formula. The distance formula for 2 points which are connected by a line segment can be computed as this. We have the square root of this formula, x sub 2 minus x sub 1. You square that, plus you also have y sub 2 minus y sub 1, and you square that as well. The entire expression, including the radical expression or denotation, is on its distance or the length. So let's try to solve first the distance of points A and B, or the length of segment A, B. So let's pick here point B as our second point, so it would include our x sub 2 and y sub 2. By the way, our formula here, you could interchange x sub 1 and x sub 2, but make sure that when you do, you also interchange these 2 here. But don't worry about these 2 expressions because it is under addition, so we could have y sub 2 minus y sub 1 here, then x sub 2 minus x sub 1. Again, we're going to pick here point B as our second point, hence our x sub 2 is equal to 8, that's 8, minus our x sub 1, which is 3. You square that. Next, our y sub 2 is -2 minus our y sub 1, which is -6. You square that as well. Hence, you will have here the result. This is 5 squared plus -2, double negative property. We still have one more parenthesis here. We have -2 plus 6, that's 4 squared. So we have here the square root of, you have 25 plus 16. So the length of AB is equal to the square root of 41. That's the length of AB. Okay? Next, let's have B, C. Let's pick here C as our second point. So our C is at -1, -1. That would be our x sub 2 and y sub 2 respectively. So we have here -1 minus our x sub 1 for B, which is 8. Okay? You square that. Plus your y sub 2 is also -1 minus -2. And then you square that as well. So you will have here the square root. This is -9 square, or the square of -9. Plus, you'll have your double negative property. Plus 2, so you have 1 squared. -2 plus 2 is 1. So you will have here square root of 81 plus 1, which will give you square root of 82. By the way, for our first result, the radicand is a prime, so we cannot look for a perfect square factor aside from 1. This here, we have a lot of factors, but just for the idea of checking later using Pythagorean theorem, let's stick with that. And of course, you can simplify it further if you would like to. And finally, for our segment AC. Our segment AC, let's pick C as our point 2, so we still have -1, -1 for our x sub 1 and x sub 2 x sub 2 and y sub 2 respectively. So you have your -1, then your A is your point 1, so -3. You take the square of that, okay, plus you will have here -1 as well, and minus -6. Okay, and you square that as well. So we have here, so -4, or the square of -4, okay, plus the square of, we have -1 plus 6, so we have +5 squared. You will get here a result, which is square root of, this is 16 plus 25. So you will get the distance or the length of segment AC being square root of 41. Noticeably, we could see that our segment AB is as long as segment AC, which would mean this is an isosceles triangle because we have two sides which are of the same measurement. But that's not our concern. Our concern here is to determine whether this is a right triangle. Let us try to establish here that our segment BC, per our figure and our measurement, is the longer side, or the longest rather. This would be our, if this is a right triangle, this should be our hypotenuse, meaning this would be our 90-degree angle here. This would mean that the length of that, using the Pythagorean theorem, the square of the length of BC, according to the Pythagorean theorem, must be equal to the square of the sum of segment AB and AC. Okay? To establish Pythagorean theorem, this is what we're going to check. Okay? So we have here the square of segment BC. Let's put it here at the bottom. Okay? We have BC is square root of 82. You square that. Is it the same? So question mark. As the sum of the squares of AB, which is 41. Probably you can notice it already. Plus square root of 40, or the square of the square root of 41. This is BC. Segment BC, the square of that is equal to this. Of course, when you take the square of that, you will be removing the radical sign. So you have 82. On the other side, you have 41 plus 41, which will give you a result of 82 is equal to check mark 82. Of course, question mark here. This would mean that we have established the idea of the Pythagorean theorem, which tells us that this side, the longest side of a triangle, is, or the square of that, or the square of the length of the longest side of the triangle, is equal to the sum of the squares of the other sides. This would mean that this is really a right triangle with a 90-degree here. This would be our hypotenuse, leg and leg rather. And at the same time, not just a right triangle, but this is more importantly an isosceles right triangle, because again, we have established that these sides have the same measurements. Nevertheless, the goal for this video is just to verify whether the three given points are vertices of a right triangle, and we have established that fact here. Thank you for watching, and stay tuned for another session here in AG for Analytic Geometry.